Hi everyone, I am Jahek, an undergraduate student studying physics in the University of Malaya. So welcome to my video on making sodium chloride crystals at home. In this experiment, I will guide you through 3 different methods for growing crystals and analyze their results later on. Along the way, I will also explain the fascinating physics behind the crystallization. So without further ado, let's get started.
Here are the materials and tools that we will be using today. We have table salt, which is our source of sodium chloride in this experiment. We have tap water, containers of various shapes, a pot and a kettle for dissolving the salt. The manipulated variables in this experiment includes the way I dissolve the salt and the surrounding temperature where the solutions are kept. These factors will influence the results of crystallization, and I will show you how. Procedures. Procedure 1. Boiling water dissolution. For the first procedure, I dissolve table salt in boiling water to create a highly saturated solution. After dissolving, I pour the solution into a taller container. However, boiling causes rapid evaporation and superprecipitation of sodium chloride, which quickly led to uneven crystal formation and a cloudy solution. Procedure 2. Warm water and low temperature. In the second attempt, I use warm water instead of boiling it. After dissolving the salt, I pour the solution into a border container, and after that, I place them in the refrigerator to lower the temperature rapidly. For the final procedure, I again use warm water, but this time I pour the solution into a taller glass bottle and let the solution cool slowly at room temperature. For the disturbance in crystallization, crystallization is often disrupted by environmental and chemical factors. Let's explore 2 critical disturbances in the process. Firstly, supersaturation. When a solution becomes supersaturated, it means that it contains more solute than it can normally hold at a given temperature. This happens, for example, when dissolving sodium chloride in boiling water. Rapid cooling after such a state leads to a disordered precipitation because the solution's concentration changes too quickly for the ions to settle into a regular lattice. And also, this chaotic environment encourages random aggregation of sodium chloride ions, forming cloudy and uneven structures instead of a sharp, orderly crystal. The second critical disturbances. Surface nucleation during boiling. During boiling, tiny disturbances such as temperature gradients at the surface encourage premature crystal formation. The evaporation at the surface causes slight cooling, leading to the emergence of small nuclei. These early forming crystals often trap air bubbles or contaminants, disrupting the alignment of sodium and chloride ions. As a result, the nucleation process is uncontrolled, producing floating, irregular crystals that cannot grow into proper cubic structures. For the true crystallization mechanism, firstly, we have Le Chatelier's principle in chemistry. When the solution cools, Le Chatelier's principle comes into play. It predicts that as the system loses heat, the equilibrium shifts to favor the exothermic reaction, where sodium and chloride ions combine to form solid crystals. Slow, steady cooling, such as placing the solution in a refrigerator, lowers the solubility gradually, giving ions sufficient time to align in an orderly pattern. Secondly, sodium chloride's striking cube structure originates from its face center cubic, or in other words, FCC lattice structure. This structure is governed by the alternating arrangement of positively charged sodium ions and negatively charged chloride ions. There are equal bound strengths and consistent spacing between ions, creating a symmetrical and stable cubic lattice. This symmetry reduces the energy of the crystal system, encouraging the development of sharp, predictable faces in the final crystal. And thirdly, about the transparency of sodium chloride crystals. The stunning transparency of sodium chloride crystals comes from the flawless alignment of ions in its lattice. However, if impurities or defects are present in the lattice, they scatter light and cause cloudiness or opacity in the crystals. Now, let's take a look at the results. For procedure 1, the boiling method resulted in dense precipitation, but the crystals were uneven and cloudy, that are not ideal. For procedure 2, using warm water and refrigerating the solution produced a single clear sharp-edged transparent cubic crystal. This method demonstrated a good balance between temperature reduction, but the crystallization rate is low. For procedure 3, by dissolving salt in warm water and then letting it crystallize at room temperature in a taller glass bottle, I obtained many almost cubic crystals formed along the string suspended in the solution. Here is a close-up view of the crystal from the procedure 1 to 3. The procedure 2 yields the clearly noticeable cubic lattice and sharp edges.
In this video, I demonstrated 3 different methods for growing sodium chloride crystals and explained the physics of crystallization. Although the 3 methods show different rates and qualities of crystallizations, the second and third methods gave the best results. I hope you learned something useful and enjoy the journey of growing crystals. And if you liked this video, don't forget to like and share. Thank you for watching and good luck with your own crystal growing experiment.